So I was looking at some of the previous Phylanx seminar talks, and I realized this is very different from that. So just bear with me. I'll try to do my best, and of course, ask anything you want. Just interrupt me and ask. I don't have much slides, so we have plenty of time. Okay, so let's begin. So today I'm going to talk about two mathematical formulation of tiling problems, which you guys were working on in terms of how to distribute arrays, matrices, and other such structures across multiple nodes in a distributed set. But before we can talk about it, I'll just going to kind of skim over some of the basic terms and stuff. And I do not have too many figures in the slides, but don't worry, I can draw it whenever I want if you have any questions. So I'm trying to use that. Okay, so let's start with what a hypergraph is. Okay, so here's an example of a hypergraph. Ignore the numbers in those vertices for now. They have no bearing on what I'm going to talk about. I was using another example from another problem where I actually had numbers on the vertices. But generally, the idea is this. The dots are the vertices, just like graphs. But instead of edges just connecting two vertices, you have hyperedges, or more general edges, which can connect more than two vertices. Right. So, for example, say you have say you have this set 9, 11, 8, and 18, right? And they form this hyperedge B. So it's just a very simple generalization of graphs where you have on the edges with two or one vertices to more than. So here's some definitions. A hypergraph is a set of vertices V, and along with a collection of non-empty subsets of V, as I was showing. We call a subset E an edge or an hyperedge. A graph is a special type of hypergraph where you just have two edges or one edges. So one edge would be a loop or a self-loop. Since we are going to talk about computations on hypergraphs and graphs, so we assume they are finite. Most mathematicians work also with infinite graphs. So we are not working on infinite graphs. We generally use the size of the vertex set denoted by n, and the number of edges denoted by m. Ignore the p. That's really
What's the p?
P is basically the generalization of the sum of the degrees. So it's for the hypergraph, it's going to be the sum of the cardinalities of the hyperedges. And for graphs, it's just the sum of the degrees. Here are some assumptions we make in terms of hypergraphs. All hypergraphs here are undirected and connected. Maybe we can ignore connectivity. So in terms of hypergraphs, so for graph, connectivity is easy, right? If I have a graph like this, this graph is connected, it's a tree. From any pair of vertices, there is a path. For hypergraph, it's defined kind of similar way. If you have a sequence of hyperedges between two pairs of vertices where every successive edge, correct me if I'm wrong, has a non-empty intersection, then the hypergraph is connected. So for each vertex, we can have a weight function associated with it. So it's like a weighted graph. So in this example, I put integer weights on the vertices. I can put weights on the edges. And a graph may be both vertex and edge weighted. And we may use this type of formulation later in how to characterize styling.
So you're equating a weight and a color? Is that what you're saying?
You could if the weights have like this fixed come from a fixed domain, integer domain. So it's like say you have the weights could be either 1, 2, 3. You might as well represent them with red, blue, and yellow and stuff. So let's define coloring because we do use the notion of coloring. A k-vertex coloring of a graph is a function so which assigns a color to every vertex. Now suppose I have a graph right? So and I have two colors. So I've colored this red and blue. Now you see, according to this definition, this is not a valid coloring because you have reds which shares an edge or a blue which shares an edge. But could you color this graph with two colors? Right, you can. Now for hypergraphs, you can define colorings in many ways. I am giving two specific definitions. One is strong coloring. So in the strong coloring, suppose I have a hyper edge like that, then I have to use at least 4 colors because every pair of vertices must have different colors. That's a strong coloring. So for all the vertices that participate in a hyperedge must have a unique color. And the weak coloring is like where there must exist at least a pair of vertex that have different colors. So in other words, each hyperedge cannot be colored by just one color. At least 2 colors need to be. And for the purpose of tiling, we are going to use weak coloring. So when we talk about coloring, we just, and if it's for a hypergraph, just assume it's a weak coloring. Okay. Let's define what a constant satisfaction problem. When I say CSP, what I actually mean. There are many ways to, I guess, define it. So here I am defining it using a well-known formulation from a few years ago. Okay, so in most general setting, you have a set of, I will give you an example. So you have a set of variables x. So suppose x is three variables, right? And you have a collection of functions. So for now, just assume D is just 2. So we are only working in Boolean functions. So for simplicity, let's say x is XOR, just x, or 1. So I have 2 Boolean functions there. That's my set F.
What is k in your case?
So k could be the arity of a function, particular function. Now, if I say, instead of saying XOR, I said XOR 3, what I'm then doing is I'm restricting the number of variables to XOR to at most 3.
And then k would be 3.
K would be 3 for that particular function. Yeah, I think this definition is a little restrictive. It's depends on the function. But for each set of function, you have the form. Now suppose it is 3 and the odd is 2. So the arity of odd is 2 and the arity of XOR is 3. Using these two functions and this set X of variables, now remember the X determines the input size. Right, so this is where the size of the input n comes from, and it depends on the instance of a problem. I can create a constant CSP as like this. Right, so in the first case I used the XOR, and the second case I used an OR function. And so this CSP is a specific instance of the problem defined by F. So basically F defines the problem. For different types of constants, we get different problems. We have SAT, which is going to be, we can represent SAT as, actually this is not correct. It's the way we do it is like this. So this indicates that the first I variables in the OR clause is negated, and the first j variables of the OR clause is negated, and the OR clause has size I. So for example, if I have, this is 3 and 1, then this problem becomes 3 set. And I can have formulations like x1 or
I'm sorry, what does the comma 1 mean again?
so this comma means that the size here, the k is 3, and the first variable is negative.
Okay, first.
Yeah, so depending on, so in the OR you could have in a general SAT you can have negative literal. So it just OR doesn't give you that SAT. But again, there are many ways to define constraints based on the functions.
So the only thing, you have the two parentheses, and they differ in order. So you have 1, 2, 3, and 2, 3, 1.
Oh, this is just a trivial example, but the variables could be different as long as the first one, it's the way to express it in a syntactic way. It's just, it doesn't have a,
Are those two instances, or are those multiplied together?
oh, these are conjunctions. So I did ignore that very important.
Is that one a conjunction too?
Everything in CSP, I'm talking about conjunction. So when you talk about constraints like this constraint, so there are many ways to define the CSP problem, which I'm going to talk about next. And these, and based on those objectives, we need to satisfy these constraints. So what's the first one?
Excuse me. It's probably just a notation, but CI is FI and set of perhaps ordered XIs, right? Not just XI. It's a set of XIs, right?
It's a set of XI, set from XI. It doesn't have to necessarily be ordered, but that set.
Oh, it's just not one element, it's a set of, a
Yeah,
subset
yes,
of X.
it's a set of XI.
And perhaps ordered, right?
Well, not necessarily,
on the
because
function.
most of the Boolean functions would, for example, if it's an OR function, right, the order doesn't matter. But that, say 1, 3, and 6, those 3 variables are involved, and that's your XI. Okay, so there are many ways, so there are many objectives when you have a set of constraints. First is the most well-known one, is called the satisfiability problem. So here the goal is find an assignment that, or say there is none, which satisfy all the clauses. The second one is an optimization problem, which is the max version. Find an assignment which satisfy most at maximum number of clauses or constants. The third version is a minimization version. Find an assignment which and we'll finish the sentence. So the maximization version is find an assignment which satisfies the maximum number of constraints. What's the minimization version?
Minimum number of constraints.
No, which minimizes the number of unsatisfied constraints.
Minimizes the number of constraints.
Let me ask you this. Are these two equivalent?
Kind of equivalent, right?
They are equivalent in terms of exact computation. Because if I find an exact solution for satisfying the maximum number of constraints, which also makes the number of constraints which are not satisfied minimized. But as you will find later, when we talk about approximation, that's not necessarily true. So everybody here, I assume, is familiar with NP-Hardness? Okay, let me start. So I'm going to draw the most common drawing everybody does here. Okay. So in computational complexity, we define, first of all, this slide I'm only going to talk about deterministic algorithms. That means given an input for a problem, we only care about algorithms which does not make random choices. So if you give the same input, it will always result in the same sequence of execution and it will give you the same output. No randomness. If you add randomness, becomes more complicated. Anyway, so a problem is, say, is in P or is solvable in polynomial time if there is a deterministic algorithm for that for all input of that problem, it can give you the correct exact output, which has a function of this form, where n is the size of the problem and c is a constant. So it's a polynomial in the input size. Our problem is in NP if, for that problem, if somebody gives you a solution to the problem, you don't know how they found it. So just somebody just gives you the solution. You can verify whether the solution is correct for that particular input in polynomial time. So for example, suppose you have a graph and you want to color, somebody asks you, can this graph be colored using 3 colors, red, white, and yellow, right? So what would be a solution for that? If somebody gives you a solution for that particular graph, how it will look like? Well, it will look like for each vertex, there will be a color assigned to it, right? So for each vertex and color, there is the vertex color pair. And can you verify whether it's a valid coloring in polynomial time? Yes, easily, in linear time, right? You just check for each edge whether the colors are different, right?
So it's quadratic time, not linear. It's quadratic time, not linear time.
Well,
it's a number of vertices
yes
times
and
the
no.
number of
In graph algorithm, because the input size is the sum of the vertex plus edges, and because it runs in the number of edges, it's still linear.
For each edge, you have to check all the vertices.
No, the edge has so I'm just talking about graphs. So each edge has only 2 vertices.
Still have to check for all the vertices. So it's
No,
at
so
least-
you go by edge wise, right? So there are m edges, and it takes odd
Oh, okay,
rank.
so it's twice. Yeah.
Yeah.
Okay, k is 2 for normal graphs.
Normal concept.
Yeah. Okay.
And in for hypergraphs, it could be at most n times n. Each edge could have at most n. But either case, it's polynomial. But if somebody asks you, can you find a coloring with 3 colors? That seems quite difficult, right? So as everybody knows, coloring problem, so those type of problems are known to be NP-hard, where right now you have somebody gives you a solution, you can easily verify it, but it's hard to actually find a optimal solution. Actually, I wasn't really technically correct what I just said one sentence back, but for our purpose, I don't want to recorrect myself and make it more confusing. So NP-hard problems, we do not have polynomial time solution, exact solutions. So obviously the question is, what can I do? Because as we all know, we may never be able to answer P is equal to NP in our lifetime. And suppose somebody comes up with an answer for P equal to NP. It's a kind of philosophical question. Do you guys know what P equal to NP problem is, right? Okay. So basically this says that so I drew these 2 circles, right? So P problems for which you can always find a solution in polynomial time. There's an algorithm, deterministic algorithm, which finds a solution in polynomial time, falls into this set P, set of problems. And I have drew NP as a slightly bigger set. The P equal to NP problem or P not equal to NP problem is to say whether or not P is strictly smaller than this set NP. So does there exist a problem for which there is no way we can find a polynomial time algorithm? Funnily enough, there have been numerous counter progress in this domain. What I mean is that people have come up with techniques and have shown that this kind of technique will not work in proving this. It's a very unusual type of research where you come up with extremely complex technique and then show that you can't work using this kind of technique. So I'm not going to talk about it. But anyway, so that's the central problem in computer science. But what about approximations? So okay, we can't find an exact solution. So if the graph, you're given a graph, somebody asks you, can you color it using 3 colors? Okay, I don't care if I can color it using 3 colors. Can I color using 6 colors? Right? That might be works for us. I mean, it's fine for us if it's that good. But it turns out for certain problems, it's not even possible to find, for example, the coloring problems. If somebody asks you, can you color it using 3 colors? You can't even tell him for certain you can color it using 6 or whatever constant you choose. It's so let's start. That's a good segue for what is approximations. Okay, so suppose P is some NP-hard optimization problem, as I was talking about here, and A be some algorithm that approximates P. So what I mean by approximates is this. So A outputs some value. So remember, we are trying to minimize something here. I can define the maximization problems in a similar way. So for the coloring, right, so you are given a graph, and the question is, what is the minimum number of colors you need to color the graph, right? And so that would be the optimal value for the P, for the coloring. And the output of A is something else. And the ratio is the approximation ratio for that algorithm. And for minimization, it will obviously be greater than 1. And we have some constraints. First, that A must script, they must run in polynomial time because we really don't care about exponential algorithms. Then we can probably solve it exactly right. We do allow it to be randomized. So the algorithm can make random choices. It's an open question whether randomization helps, and we don't know that. It's widely believed that randomization has no power over deterministic algorithms. But it has been shown, or at least it has been found in practice, in terms of coming up with useful practical algorithms, randomization do help. You can come up with very simple algorithm using randomized additions, which is extremely hard to replicate without the randomization. I'll give you a trivial example. Consider a SAT problem, right? You have a sequence of right, so consider a SAT problem where you have a sequence of constraints. And you know that each variable can either take 0 or 1 value, right? Now pick a random assignment of the values, right? So you choose for each variable, you choose a random 0 and 1. Now ask yourself this, it's a trivial calculation. And suppose each clause, each constraint has at most 3 literals. In average, how many of these clauses will be satisfied? So each clause here has, say, 3 literals. So add another one here. Right? So, and you're going to pick a random assignment. So for each variable, you choose 0 or 1 with probability higher. So in average, how many clauses will be satisfied? Well, it's easy to see because the only time when an OR clause is not satisfied when all is 0. Right, if you choose a random assignment of 3 variables, 7 out of 8 times, it will be satisfied. So on average, 7 out of 8 clauses will be satisfied. And so you get a 7 out of 8 approximation ratio for the maximization version of the problem, where you have to satisfy the maximum number of clauses. Now here's things get interesting. What if I want to minimize the number of unsatisfied clauses? Can you use the same idea of randomization? I'll not answer that, I just leave it as.
That's unfair.
Well, that's how. Well, the answer is no. It becomes complicated from innovation. Okay, so hardness of approximation. This is where things becomes much more interesting. So remember, I was drawing this picture where I was saying you have P and you have NP, right? Now here I'm looking at this entire set NP, which of course has P inside. Actually, I can make P here somewhere. Okay. Now in terms of, so suppose I have all these problems which I discussed, these are NP-Hardness optimization problems, whose decision versions are in P. But in terms of approximation, they map into different strata of these circles. What I mean is this. Let's start with the first sentence. FP-TAS means fully polynomial time approximation scheme. What it means is that for that particular problem, remember the approximation ratio I was showing in the output value at that? I can make that arbitrarily close to 1. There is another way to define it. this FP-TAS, and I think in Wikipedia and stuff it defines in terms of the error rate and stuff, but these are kind of equivalent. So these are the best we can hope for an NP-hard problem where we can't get exact solution, right? If I can reduce the alpha as close to 1 as possible for all practical purposes, that's great, right? Unfortunately, there are many problems where you can show that's not going to be true. So there will be some absolute constant. Beyond that, you can't get better approximation. For example, this SAT problem, max SAT, maximizing the number of satisfied clauses, has a bound. You can't have any approximation algorithm that performs better than that alpha. And for minimization problem, we'll have a lower bound like this. So then we say P is alpha star approximation hard. That means there's no polynomial time deterministic algorithm can give you a guaranteed solution which is alpha star way less than alpha star way from the optimum. Now, if in terms of approximation hardness, we can kind of create a hierarchy of different complexities. So here at the center, we have P, which is the same as this, which means that it has an exact solution in polynomial time. So alpha is 1. Can't get better than that. Then you have FP-TAS, which I haven't drawn. Then you have P-TAS, where there is a bound on alpha, which you can't make arbitrarily close to 1. And as we increase alpha, we get harder and harder approximation problems. Okay, so now completely change the subject. So that was just the preliminary. Now we're actually going to talk about time. So here's a simple example. We have 2 processors, right? And I have 3 matrices, A, B, and C. And I have, the tiling is basically a type of partitioning the matrices into different processes. So here I have taken the 2 columns of A and put it in 2 different processors. Similarly for C, but for B, I have taken the 2 rows and put it into different processors. So for the first case, we say it's a column-wise tiling, and for the B, it's a row-wise tiling. Now I model that basic idea in a more mathematical form. So suppose I have k nodes, P1 to Pk. And let A be some d-dimensional array of that. So here I can consider any arbitrary dimensional matrix. It doesn't have to be 2-dimensional. So a tiling basically would be a function of, so basically this weird notation basically means is this. You pick an element and it maps to a particular processor. That's all it means. So let's look at 3 simple examples. Simple special cases. If suppose A is 1-dimensional, and in most cases it's a nice assumption to make because ultimately all arrays are kind of 1-dimensional in some sense. I mean, the structure is just a higher order structure. So we can just think of each element is mapped to a processor, different processor. So many elements could be mapped to a same processor, so that's also fine. Now if we allow copying, so suppose we want to reduce the communication cost, and so there might be multiple copies of the same element or the same block in different processors, then it becomes a function from n to the power set of p, and so on and so on. So this is the most general way you can define tiling as a function or a mapping of elements of the array coordinates to different processors. So any kind of tiling can be mapped in this general form. Of course, row and column tiling are 2 special cases. Okay, so tiling cost. So there are many ways to define it. here we look. Here we're just making this very basic model. So if if the ith element of A and the jth element of B is this tiling, but they're not equal, that means they are not in the same processor, right? Then we say they incur some cost. That's the, if they are in the same processor, they don't incur any communication cost. That's our assumption. If they are not, they may or may not incur some cost. So that's the very basic assumption.
It's dangerous to talk about atomic operations because computer scientists might misunderstand what you mean.
Yes, I should point out these are all in random access machine model I'm talking about. So I guess addition, multiplication, and stuff like that. So remember, these are just elements. These are not matrices.
I know. But an atomic operation, at least in our domain, is something different from what you have in mind here.
Okay, I see what you were saying. I mean, well, I could say these, let's just call it arithmetic operation, something. But it could be other stuff, like it could be comparisons too. So that's why I kind of like put a black box thing. It could be anything. But as long as if they're in the same node, then there is no communication in terms of distributed computing, and if they are not, there may not be a communication. So that's the really basic model. Okay, so what we have here is this. Tiling cost is basically the cost of communication given a specific tiling configuration, right? So for each, A, B, C, dot, you have TA, TB, and so on, right? And suppose you have a fixed sequence of arithmetic or any kind of operations that do some stuff on them, which would involve computation between pairs or triples or whatever of elements of these matrices, which gives rise to this communication cost based on TA, TB, and so on. We do not, however, consider the cost of creating a tiled array, because that's more of an allocation problem. Because if a matrix needs to be tiled, then you have to do what you have to do to tile it and partition it and distribute it, right? It's more of a architecture thing. It's not an optimization problem.
What about retiling necessary?
That's a good question. I'll talk about it later. So that's ignored, and so there's some reasons what I mentioned here, that these are unavoidable, could be considered to occur infrequently, and also it is reasonable to assume that the cost of different tilings are the same. So if there is not much decisions we are making. So if we decide to tile A, the cost of tiling it column-wise versus cost of tiling row-wise in most cases would be same. So suppose we are reading something from a disk and stuff like that. But ultimately, the main point is a different type of problem than the tiling problem. Okay, so now, I was going to talk about two different problems. So this is the first version. This is the version which was, Stefan was kind of working on this preliminary version of this. It comes from it's actually also, it's like a generalization of that Spartan version which so it has that lineage from that. Okay, so in this particular problem, you have a set of arrays scripted, which you want to tile. A fixed set of tiling functions, so it is like row-wise, column-wise, blocks, say those three. And you have a set of matrix array operations, and you have a set of constants, which basically said if I perform an operation, say multiplication, on a subset of A, say 2 matrices, this cost something depending on what the matrices were tiled. I will give you an example, not worry. Okay, this I'll talk about it later. Let's ignore that. Okay, so here's an example. So I have 3 matrices, A, B, and C. And consider a straight line program. I am abusing the term straight line programs. It has a different meaning. But for now, it basically means a program doesn't branch or doesn't have recursions and stuff like that. It just follows a straight line. So you have 4 operations here. I am not defining the operation, but just generic operations. And the cost is basically, you take the, so for operation 1, you take the 2 tiles of the matrices involved, or the arrays involved, and the operation, and you get some cost, depending on the tile and the operation. And you want to minimize the total cost. So this is a very, very generic formulation. You really can't, you can use heuristics and stuff like from soft computing domain, like or a gradient descent, local search and stuff to solve this type of problem, but these are not something you can model in a computation complexity sense and solve and give some hardness values. So this model doesn't consider loops and so, but again, you can augment this anyway. If you have loops, suppose this operation 1 is in a loop which runs 10 times, you can multiply the cost. You can model recursion using composition of this call function and so on and so forth.
How do you define the cost if you don't know if you need to communicate or not? In the last page. I'm not quite sure if I understand what's T of A.
So T of A and T of B are the two tilings for A and B. And the cost of applying operation 1 to A and B depends on the tiling.
It depends on the tiling of T and
no, it depends on the tiling of A and B, which is denoted by TA and TB.
Okay.
Okay, let's look at a very simple example where we have only unary operation, not even binary operation, just unary operations, where you have either A transpose B or A equal to B. So there's only these 2 operations where either you assign the same matrix to another matrix or you just assign the transpose of it. Now if TA and TB are same, then A transpose B will cost you, most likely will cost you, because Bij has to be assigned to AJI. So if TAIJ doesn't map to TBJI, is not equal, there is a communication cost. So if
Sure.
not clear?
But the next line is, you say the opposite thing.
However, for A is equal to B only.
Second bullet is for transpose.
The
Third one
second is for
for-
transport. The first
Oh,
is
the
for
third one is
distinct
for
form.
assignment.
Yes.
Okay, I see. It said consider operations of the type on the top. Oh, you put it in.
Yeah, I just put
you
it,
wrote
yeah,
that
that was
in.
missing,
Yeah,
sorry.
okay, I see.
Okay. So now let's make we assume that. So this we already did, equal and transpose. Okay. Now we can kind of now go away from this styling setting and go to a graph setting. So how this works? Okay. So the first type of communication, or the cost, where you have assignment, we could model it as a constraint where if all the so this can also be modeled as zeros and ones. So TA comes from, or TB comes from this domain 0 and 1. So there are two types of, so simplicity as in there are two types of type. So it's also in a binary domain. And the first type of constraints where you do not have a communication cost if all have the same type. So all are 0 or all are 1. So all are, say, row-wise or all are column-wise. Or you have a communication cost if there is a different tiling between any pair. Similarly, we can define another set of constraints, not all equal, where cost is 0 only if there is a differing tiling. Kind of models the transpose. Okay, so this kind of creates an interesting problem which is known as, well, min-cut problems, or min-uncut problem on hypergraphs. I'm actually going to have to explain this. What are these things? So let's keep this for now. We don't have time. Okay. So how do we model this special case where there are two types of constraints? For all equal constraints, you have a cost if they are not all equal, and for not all equal constraint, is the opposite. For the case of graphs, where all the constraints, all equal or not equal, has only two variables, it's this problem, min two linear. Lin stands for linear, or also it is known as the min uncut problems in graph. So what is this problem? Let's not worry about this. Let's look at a graph. So given a graph, right, I have colored the edges with two colors, one using solid lines. So this is the min uncut problem, and others using dashed lines. And goal is to find a cut. Everybody knows what a cut is? So cut is basically, in the simple sense, is just a bipartition of a graph. So you take the vertices, you partition into two parts, that's a cut. So here this is S and the other one is going to be this. And the goal is this. For the edges which are solid, they have a cost of 1 unit if they do not cross the cut. And edges which are dash has the opposite effect. They have a cost of 1 unit if they do cross the cut. This, as you could see, is equivalent. Well, it takes 2 or 3 minutes, but you can see it's equivalent to the tiling problem of all equal and not all equal. Okay, so I am moving faster, but that's unfortunate. Okay. So as I was just mentioned, this 2 lin 2 or min uncut is actually equivalent to the tiling problem where you have only 2 matrices per operations and the cost is defined the way we had defined. Now this is what the thing is interesting. Even for this very simple case, we know that it is approximation hard for some constant alpha, so you can't, it doesn't have an FP test, you can't get an arbitrarily close result. But it does have a square root of log n, where the n is the number of variables. Approximation algorithm. So if you have a tiling, optimal tiling, where only 5 operations have cost. This algorithm ensures that log n times 5 times some constant will be that most number of operations which would cost you in the approximate solution. Okay, so what we're trying to do is to extend this for arbitrary k. So the 2 there was the size of each of the constants. For k more than 2, it becomes a problem on hypergraphs, not graphs. And as far as I know, I do not know this has been solved or not. This is very odd, to be honest, because this mean uncut problem is it's a kind of a classical problem. Well, it's not very well known, but in terms of approximation literature, it's quite common. So it's very unusual why this hasn't been worked on, but so far I haven't found any reference to it. So this seems a promising way to extend this. Well, what we know is this: either one of this is true, either it also has a square root of log n approximation, that would be nice, or it is approximation hard, and the approximation ratio is quite bad. So 2 to the power square root of 1 minus epsilon n is bad.
Epsilon is small,
Epsilon is a constant. So
but it's a constant that's just any constant between 0 and 1, or?
there is, so basically the way they say there will be some constant for this is true. So say epsilon, take epsilon as a half.
Okay.
So it becomes 2 to the square root of log n, which is that. I don't think I have time to explain why we are not talking about maximization, but
Indranil, why don't we plan for a second continuation of the seminar next week, so you don't have to rush through things?
maybe week after next week.
Oh, that's fine.
Okay,
Sure.
sure.
So let's not squeeze everything into one.
Perfect. So any questions? I can stop right here, and any questions and stuff. The deletion thing, then I can talk then, because it's a quite interesting problem. No, sorry, deletion. You mentioned about retiling thing. That has some relation to deletion and stuff. Then I can add that to the next one.
Okay.
Anything else? Oh, obviously I haven't talked about what kind of techniques are used to solve or do this type of results.
So what I'm hearing is that you still hope that there's a way to find a non-NP-hard problem in our case.
No, there's no hope there. What we
I mean a non-NP-hard approximation, if that's the correct term.
that's
if you
not
see what
exactly a correct term, but I see what you're saying.
Yeah.
Yes, it's actually the thing is very interesting. I was talking about this with Govi the other day. Initially, I thought this problem falls in this category, but now I'm actually starting to think it might be this. So, at least for the very simple case, we still may have hope.
Okay, good.
But obviously, you could imagine these are asymptotic results, have no real implication if you have 5 matrices, if you have 10 matrices. That's why these guys comes in. I'm looking at you. So.
Okay.
So it's kind of, we try to understand the status of the complexity. Is the reality here? It's not what you hope. It's to understand what is the status,
Yeah.
whether it's hard or easy. Well,
That was more my question, whether there's still hope that we will be able to find, to answer that question you posed. So can we map that to something? No.
We do want to map it to something known, but also we want to map it to something that has not yet been solved, and so we can solve it. That's
Sure, I mean, you're a postdoc, you want to write papers, yeah, I understand that.
So if it's already mapped to something solved, then we really don't care in terms of theory.
Well, even that answer would be nice for us, right? If you say, that has been solved,
Unless the mapping is very complex itself, the mapping procedure is some, then yes. But otherwise, nobody cares.
Okay, good.
There is a term in theory that the stuff we do is considered galactic. Well, the algorithms we propose are considered galactic algorithms in the sense that they only benefit if the data size is of the size of the galaxy.
Okay. So
So
you probably will not have that amount of data to deal with.
But that's the domain. The thing with I mentioned this in passing when I was talking about these very generic formulations with all kinds of things you can add weights and all that. There is this domain of soft computing, right? They use evolutionary algorithms, they have whatnot. You have hill climbing, similar in annealing and all that stuff. So when you have a black box problems like that, they try and this is like a needle and actually needle in the haystack is not a right example because you can use a magnet, but you see what I'm saying, and so that's a different domain. But in terms of computation complexity and algorithms, we want to have more hard, concrete results, which makes it we have to make restrictive assumptions. Otherwise, there's no structure.